All right, good afternoon, everybody. Let's get started. So today what we're going to do is we're going to begin learning about all different types of memories and what different applications we might want to use them for. And so we're going to start off just looking at this list of different memory technologies. And the first thing that I want you to notice is just as you go down this table, basically your capacity is increasing potentially dramatically. So we'll start with the very top, which are our registers. And so the registers are something that we're familiar with, which we said the registers are very fast. The problem with the registers is that we can only have a small number of them, okay? And so while we get a latency of around 20 picoseconds for our registers, we can only have, a handful of them, or say like 32, like in our RISC-V processors. And so we can't store a lot of data in our registers. In addition, if you look over here at the cost column, you see that registers are also very expensive. So moving down this table, the next type of memory that's available to us is what's called SRAM. SRAM stands for Static Random Access Memory. And in today's lecture, we're actually going to learn about the difference between all of these technologies, at least at a high level. And what you see right now is that now we've been able to increase our capacity to kilobytes and even megabytes. And we've paid a little bit in terms of our latency. We've gone from picoseconds to nanoseconds, okay? So moving along, the next type of memory technology is DRAM, which stands for Dynamic Random Access Memory. And it allows for even more capacity than the SRAM. So now we're up to orders of 10 gigabytes. And we haven't paid too much in terms of latency, about 1 order of magnitude between the SRAM and the DRAM. And finally, we have what's called non-volatile memory. So the flash and the hard disk have a little star next to them to indicate that they're non-volatile. What that means is that even if you power your machine down, it's still going to be able to maintain the values in those storage elements, whereas our registers, our SRAM and our DRAM cannot do that, okay? So flash is going to get us, up to hundreds of gigabytes. And finally, our hard disk, you can almost think of it as infinite storage, where we can get terabytes out of it. But of course, the main problem with the hard disk is that it's really slow. We're now on the order of milliseconds for access time. All right, so we've got all of these different types of technologies, and we want to think about, how do we use them together? So the first key insight is to realize that the different technologies are good for different applications, and so we're going to use them in that way. So the first way that we've used them is, as we've seen, we've put registers in our data path, okay? So the registers, which are able to store data and be accessed really, really fast, are great to have in our data path for all of our instruction computations so that we're able to minimize our clock period of our processor. But we can't have very many registers, and so certainly we're going to need some additional form of storage. And so then we move on to our SRAM and DRAM technologies. And so now we can have on the order of gigabytes of memory. But of course, we're paying a little bit in terms of speed. And so we're going to see in today's lecture how do we deal with that. But basically, our main memory, both our instruction memory and our data memory, are going to be made of these SRAM, primarily DRAM, but also SRAM technologies. Okay, and finally we have our flash and our hard disk. And so this is basically all of your sort of secondary storage, data that you don't need to access very frequently. And so we call this the I/O subsystem, which we're going to learn about in next week. All right, so let's go ahead and take a look at how each of these technologies works, just so that we have a sense for why one can handle more capacity than another, why the latencies change, things like that. So just a quick note. for the rest of this particular section of today's lecture is not on the quiz. It's just meant to give you guys some information into how these different types of memories work. So sit back and enjoy. But the part after that, we'll go back to material that will be covered on the quiz. All right, so let's talk about these memory technologies. So we're going to start with your SRAM, which stands again for static RAM. Okay, so an SRAM looks something like this. You've basically got an array of cells. And here we're just showing you a very small SRAM where you've got 8 rows of information, and each one of those rows has 6 bits in it. Okay, so we have in this example an SRAM array that's of size 8 rows or 8 words by each one is 6 bits wide. Okay, so what else is here? We have an address decoder where if we give it 3 bits, we can select one of these 8 rows in our SRAM array. And so decoders is actually a piece of combinational logic we haven't really seen too much so far. But basically what it is if I give you an encoded value, it's going to set it has basically 3 bits of input, but it has 8 lines coming out. And whichever row I select, so if I say, for example, address is 001, then it's going to make this row have a value of 1, whereas all the other ones are going to have a value of 0. Okay? And we're going to see how that gets used in just a minute. All right, and so each of these horizontal lines are what we call a word line. So it corresponds to one piece of data that has multiple bits in it, and we use that address decoder in order to select which of the word lines we're trying to access. Then each of these little orange boxes is an actual SRAM cell, and in a second we're going to blow it up to see what each one of those looks like. And finally we have, these vertical lines, which we call bit lines, and they're basically going to be used in order to both input new data into these SRAM cells and read data out of them. So when we want to read data out of them, the data is going to come out through these sense amplifiers over here. If we want to try to write data, then we're going to put new data in over here at the drivers, and then the drivers are going to force the new value into these SRAM cells. And now let's take a look at how actually all of that happens. All right, so first let's take a closer look at what an SRAM cell looks like. All right, so it's a 6-transistor cell. So from this picture, first of all, who can tell me where the 6 transistors are coming from? Yep.
2 in each inverter, and then it's 2 in each cell.
Exactly. So I have 2 inverters, which we've learned from our CMOS lecture that are each made up of 2 transistors, one PFET and one NFET. And then we have these 2 additional NFETs on the side. So let's first see what these inverters do. So if you recall, when we had our first sequential logic lecture, we saw that if you connect 2 inverters back to back, you're basically forming a storage element, because the inverters are going to make sure that, if I have, let's say, VDD on this side, then I'm going to continue to have VDD because this first inverter is going to make sure that's ground, and then that next inverter is going to make sure that I make yet a stronger VDD signal, and so I'm going to be able to maintain that value. Similarly, if I have, ground on this side, then I'm going to maintain the ground value. Okay, and so the inverters are, when they're tied together in this feedback mechanism, they're very good at maintaining a value, because even if noise is introduced into the system, it's going to continue to produce a valid output so that my representation of my zeros and ones continues to be good and valid the entire time that it's being stored. Okay, so those 2 inverters are what's actually, storing my value. And now we need to talk about how we're going to access those values. And so the other 2 transistors are these access transistors, which we see here on the sides of the SRAM cell, and they're what connect the SRAM cell to these bit lines. Okay, so now let's go ahead and see, how we would do a read using SRAM technology. So we've got here our SRAM array, and we've got, highlighted a particular bit of our SRAM array, and let's see what happens. So the first thing that we're going to do in order to be able to perform a read is that we're going to pre-charge our bit lines to VDD, okay? So notice that I have two bit lines, one that's labeled bit line and one that's labeled bit line bar. However, for reads, I'm actually pre-charging both of those to VDD, or to a logical value of 1. Okay? Now, after I've pre-charged them, I stop, I disconnect them from power. So they still have a VDD, but it's not being maintained. And so the next thing that I do is I use my decoder to pick one of the word lines. And the one that I picked is going to have this word line have a value of 1, or it's going to be VDD. So the fact that this particular word line that I picked now has a value of 1 is going to be fed to the gates of these access FETs, and it's going to turn those transistors on. Okay, remember that NFETs are on when you have 1 at their input. Okay, so what happens when I turn these on? What happens is the following. Let's assume that my static RAM cell was holding a 1 over here, and a 0 was corresponded to the inverse of the value that I was holding. And so when I connect this bit line to my actual SRAM cell, what I'm going to see is that, well, this value was VDD, and this value was VDD, and so this value is going to continue to look like VDD throughout. Okay? But what's happening on the other side? On the other side, I had preloaded the bit line bar to VDD, but the value that I had stored in my cell here was a 0. So now that I'm no longer driving that VDD, what's going to happen is that these inverters are going to slowly start to bring this value of the bit line down from VDD all the way down to 0. Now it's going to take a long time because the bit lines are, you can kind of think of them as these massive, large lines with a lot of capacitance, whereas each of these cells is very small. And so this is where these sense amplifiers come in. So these sense amplifiers are used in order to detect that, hey, I went down by a little bit of voltage. So as soon as I start to decrease from VDD, the sense amplifiers are going to realize it, and it's going to say, okay, that bit line should be a value of 0. Okay? And so it will very quickly specify that the output of bit line bar is 0, whereas the output of bit line is 1, and thus we've read the value 1. Okay? All right, how about an SRAM write? So in order to do a write, we actually want to modify what's stored in this SRAM cell. So the way we're going to do that is as follows. We're going to start off by driving, and this time holding, our bit lines to the value that we're trying to write into the cell. Okay? So if you see over here, initially my cell has a VDD, or a 1, on this side of the inverters, and it has a 0 on this side of the inverters. And I want to now flip that. Right? So I'm going to try to write a 0 on my bit line and a 1 on my bit line bar. Okay? So what's going to happen? So the next thing that I do is I'm going to activate my word line, and so it's going to turn these access FETs on. And now we want to basically try to understand, well, what happens? So what happens is that these bit lines, as I mentioned, are sort of much, much larger than the transistors in our little SRAM cell. And so essentially what happens is that the value that's being driven by the bit lines overpowers the value that's in the SRAM cell, and so it flips its value. And so essentially what's going to happen is that this ground on my bit line is going to overwrite this VDD that I originally had stored here, and now I will have written a value of 0 to this cell. Okay? Any questions about that? All right. So one key thing to notice here is that, I'm kind of describing all of this at a very high level manner, but in order to actually get these SRAM cells to behave correctly, where we are able to, read values without overwriting them, but also be able to write values at the same time, we have to basically size these transistors very, very, very carefully, and that's what this comment in blue is alluding to. All right, so now let's talk about multiported SRAMs. So far, I showed you an SRAM that allows you to either read one value or write one value, but not multiple values. So we want to consider, what if I want to be able to read or write, multiple values at the same time? Let's see how I'd have to change this SRAM array in order to support that. So suppose that I want to have 2 ports. What am I going to need? First thing I'm going to do is I'm going to have another address decoder. Then I'm going to have another set of word lines that are set by this address decoder. And then I'm going to have another set of bit lines. And then I'm going to have another set of drivers and another set of these detectors at the end here that are going to amplify my signals. And so by looking at this, we can very quickly see that this thing is going to grow pretty quickly. So specifically, if I look just at 1 bit and I'm trying to support n ports, what's happening here? So how many word lines do I have to have in order to support n ports? N, right? How about the number of bit lines? Yep, 2n. And how about the number of access FETs or access transistors? Also 2n, right? So, okay, well that's all great, and so we know that this thing, grows linearly in terms of all of these things that we need. But what's actually really bad is that the wires end up dominating the area here. And so you end up with an area that's proportional to n squared rather than n in terms of how it grows. And so basically the point of this slide is just to make you realize that that adding additional ports to our SRAMs is very, very costly in terms of area. And so we're not necessarily going to want to do that. All right. Okay, so this is just a summary. I think we can skip that. So now we want to ask ourselves, okay, so we have an SRAM cell which consists of 6 transistors. Can we do any better than this? Okay, so this SRAM cell is smaller than our registers, but could we make it smaller yet? And the answer is yes. Okay, we can actually build a storage cell using a single transistor. And that's what our DRAM cells look like. Okay, DRAM stands for Dynamic Random Access Memory. And so let's take a look at how DRAMs work. So once again, we've got these bit lines which are used to access the value of that particular bit. And we have these word lines which are used to access which of the words in the array we're trying to access. But now the question is, if we don't have these pair of inverters which are being used in order to store the value that we're trying to save, how are we going to save it? So in a DRAM, the way that we solve that is using a capacitor. Okay? Capacitors are able to, you're able to charge them, which is equivalent to having a 1 stored in it. Or if it's discharged, then it's equivalent to having a 0 in it. Okay? So let's take a look at, how one would go about using this cell. Actually, sorry, let me first talk a little bit about how these are actually designed in the chips. And so what's typically used for DRAM cells is what's called a trench capacitor. So basically this is showing you a portion of a silicon die, and up on the top is kind of our surface area, which has just got a bunch of these access FETs, and then these big deep gray lines correspond to our capacitor. Okay, so why do we make the capacitor, be this very big deep line? The reason that we do that is because the larger that our capacitance is, the better we're able to store charge. And so how do we make capacitance larger? Well, a capacitance is proportional to the area of the capacitor plates. Okay, so what these trench capacitors allow us to do is make the area of the capacitor plates very large while not changing the surface area much at all. So basically the size of the access FET doesn't change, even though I'm making the size of the capacitor plates significantly larger. Okay, and so this is typically how DRAM cells are designed. So, well, what's good about our DRAM cells? What's good about it is that because of the way that they're designed, they're really, really small, and so they're much, much denser than our SRAM cells. In fact, they're about 20 times smaller than our SRAM cells. But the problem with them is that the capacitor leaks. Okay, so remember, a capacitor is not an active component, and so it's not able to, without any help from anything else, just maintain its charge forever. Okay, so what that means is that we're going to have to refresh the value that's stored in the capacitor on a regular basis, and we're going to see how that is done in a second. All right, so let's try to first understand how we would do reads and writes in our DRAM cell. Okay, so we're going to start with writes, because writes are actually a little simpler in the case of DRAM. So in order to do a write, what you're going to do is you're going to drive your bit line to the value that you're trying to write into your cell, and then you're going to activate the word line of the word that you're trying to write to. And basically what that's going to do is you're essentially going to connect the bit line to this capacitor, and you're going to, if you're trying to write a 1, you're going to charge this capacitor. If you're trying to write a 0, you're going to discharge the capacitor. Okay? And in that way you're changing the value that's stored in this cell. All right, well, what about reading? So for reading, what you're going to do is you're going to pre-charge this bit line to VDD over 2, okay? And then I'm going to stop driving that value of VDD over 2, and I'm going to connect my access FET so that now my capacitor is connected to my bit line. And what's going to happen now is the following. Well, I had this value of VDD over 2 on my bit line, but it's not being driven by anything. And then I had a capacitor which either had, no charge on it, meaning it was representing a 0, or it had some charge on it. Now when I connect the two together, if the capacitor had no charge on it, what's going to happen is that VDD over 2 value on your bit line is going to go down a little bit, and instead your capacitor is going to get charged a little bit. Similarly, if your capacitor was charged, then what's going to happen is that VDD over 2 value is going to go up just a tiny bit. And so we then use our sense amplifiers to detect which way did that bit line change. Did it increase or did it decrease? And based on that, you're able to detect whether you whether you had charge on that capacitor, meaning you had a 1 there, or you didn't have charge on the capacitor, so you had a 0 there. Okay? And so the key problem, however, is that if you look carefully at how you're doing these reads, well, when you're reading a value of 1, for example, what's happening to your capacitor is that it's getting discharged, and its charge is being shared with this bit line. Similarly, when you had a value of 0, you're actually somewhat charging your capacitor. And so basically, reads are destructive. They basically get rid of the value of your cell. So in order to deal with this, every time you do a read of a DRAM cell, you have to follow that by a write of the value that you just read. Okay? And this is what we mean by refreshing the DRAM cells periodically. That's how we ensure that we're still able to maintain that value in our DRAM cell on our capacitor. Okay, so let's move on to our non-volatile storage. And so the next technology is flash. So flash technology works as follows. Basically, you've got this, this floating gate, which is a very well insulated conductor, and you place it essentially in between the gate of your transistor and your source and drain. And so what happens now is the following. Imagine that I have some charge in this floating gate. And let's say that having charge there means that I have a 1 stored there, okay? Well, if I have some charge there, and I now essentially turn this word line on using some voltage, which in the past was able to, if I didn't have the floating gate, would have been able to turn this transistor on. Now the fact that I have electrons inside this floating gate, basically it's the voltage I was able to use before in order to turn that transistor on is no longer going to be sufficient, okay? So what's going to happen? If I apply that same voltage to my gate, the transistor is not going to be on. So I'm not going to have current flowing between my source and drain, all right? So essentially what I do in order to read a SRAM cell is exactly that, which is I apply a voltage that without this floating gate would have been able to turn my transistor on. And if the transistor turns on, then that means I had a 0 stored there. If it doesn't turn on, then that means I had a 1 stored there, okay? And basically this is how flash memory cells work. And so what's good about them is that they're really, really dense. In fact, if you go a little bit further and rather than just checking whether your transistor is on or off, you actually measure the amount of current that's produced by the particular voltage that you're putting at the gate, you could even use a single flash cell to store multiple values. Okay, so basically, if I get a small current, it might represent a 1, whereas if I get a very large, it would be the other way around. If I have a lot of charge on there, then I'm going to get a very small current, whereas if I had just a little bit of charge, then I'm going to get a larger current, and so I can have that represent different values within the same bit. All right, so, well, that's great. So the problem, however, with flash cells is, number one, they're extremely slow, especially on writes. And the reason for this is because in order to write to these cells, you basically have to go through this very strong insulator in order to write new values into this floating gate. And so essentially, it's very difficult to write to these cells. Not only is it difficult, but in fact, you can only do a limited number of writes to these cells before the transistor actually gets damaged because of the fact that you have to use really high voltages in order to overpower that strong insulator when you're writing to it. Okay, so again, just to give you a sense, what's good about this is that it's extremely dense. Bad about it is that it's slow. Okay? So finally, our last technology is the hard disk, okay? So here, what happens is we basically have this rotating magnetic platter. And the platter, based on how it's magnetized, is storing information. And then you have this head over here, which you place over the portion of the platter that you're trying to access in order to both read and write to it. Okay? So the problem with with this mechanism is that it's basically a mechanical operation to move this head to the location that you're trying to access, okay? So if I'm trying to, access a particular part of memory, first of all, I'm going to have to make this head go onto the right, track of this disk. And then after I get it to the right track, I have to wait for the disk to spin until the point where the location that, I'm looking for is right under my head. And at that point, I can actually detect what value is there. Or I can actually modify it if I want to do a write. And so, again, what's good about this technology is that it's really, really, really cheap, and we're able to store tons of data with it. What's bad about it is that it's extremely slow. However, one thing that's important to notice is that if you're doing sequential reads and writes, what I mean by that is I'm reading many memory locations that are next to each other, then the throughput of those reads and writes is on the order of about 100 megabytes per second, okay? Whereas if I'm reading just some random different locations, then my throughput is way worse, okay? We're on the order of 100 kilobytes per second. So what I want you to notice here is that basically, typically when we read from disk, because it's so much more cost effective to read a lot of locations that are nearby, and you'll see in Thursday's lecture that it actually is useful for us to bring more of these locations in. When we access disk, we typically bring a chunk of values in from disk rather than just a single value, okay? All right, so that concludes our summary of the memory technologies. Okay, so for whoever was sleeping, time to wake up. So now, let's see how we go about using these different technologies. All right, so once again here, we're just reiterating, the different kinds of technologies that we have, the capacity that each of them supports, and its latency. And what we notice by looking at this table is that if I want something to be fast, I basically need it to be, I have to accept that it's going to be small. If I want something to be large, then I basically have to accept a high latency, okay? So that's not really what I would like, right? Ideally, I'd like to have something that's both large and fast, okay? So what we're going to spend the rest of today's lecture on, and all of Thursday's lecture, is starting to try to understand how we can combine these different kinds of memory technologies so that we end up with something that's both large and fast and cheap, okay? So let's see how we're going to do that. So essentially, what we're going to do is we're going to use a hierarchy of memories that our CPU is going to communicate with, okay? So here's what I mean by that. So we've got our processor over here on our left, and it's talking to a bunch of different memories. So first you've got a small, fast memory. Then you've got, let's say, a medium but somewhat slower memory. And then you've got this really huge but extremely slow memory. And so if you put all of those together, the idea is that we want it to look to the processor as if I have a very large and fast memory. So how do I go about doing that? Well, the first thing that we're going to talk about is how are we going to make use of this hierarchy of memories. Are we going to expose that hierarchy to our processor or not? Okay? So we have two alternatives. The first is to expose the hierarchy. What I mean by that is your CPU here is going to know that it's got, this 10 kilobyte SRAM, and it knows that it has a 10 megabyte SRAM, and then it's got this 10 gigabyte DRAM and this terabyte secondary storage drive. drive. And what you're going to have to do in this kind of a setup is that it's going to be the programmer's responsibility to figure out, oh, okay, you know, I'm using this data a lot, so I better put it in my, you know, really fast memory, whereas this other piece of data I'm barely using at all, and so it can go in my slow memory, right? So sure, that would work, but that's going to make the life of our programmers extremely hard. So instead, what we'd rather do is the following. We'd like to hide the hierarchy so that as far as the CPU is concerned, it's just talking to this large memory. Okay? But in reality, what's actually happening is that it's first checking this small fast cache for the piece of data that it's looking for. If it's not there, then it's going to go to the next level of memory and look for it there. And if it's not there, you know, again. So essentially the picture looks like this. So if I say, you know, go fetch the contents of address X from memory, first thing it's going to do is it's going to say, oh, is address X in this little cache? If it is, then great, I get the answer back really quickly. If it's not, I have to go on to my next level of memory and check there. And finally, if it's not there, then I go to my really slow memory, okay? So what does this mean? This means that it's possible to sometimes get my data back really quickly, but it's also possible that sometimes I'm going to get it back really slowly, okay? So essentially, my CPU has to be able to deal with the fact that I might have different latencies in accessing memory, okay? Now, what we're going to look at next is basically memory access patterns, which we've actually looked at in the past. So hopefully this looks familiar. And these memory access patterns are basically what's going to help us realize why this hierarchy of memories can actually work well enough to make it seem like I have a very large and fast memory. So we're going to start looking at code accesses, all right? So I don't know if anyone remembers, but who can tell me what this represents? So I've got, you know, this is my time axis, and this is the address that I'm trying to access. So I have, you know, one location, then the next, then the next, then the next. Then I come back and I access those again. Then I come back and I access them again. So what does that represent in my code? Yep. A loop, exactly, okay? Now let's look at other kind of memory that we access. Well, we learned about our stack, right? And so our stack accesses might look something like this. And so what's going on here? Well, I'm accessing, you know, a bunch of locations that are nearby each other, and then I put a bunch more locations on, and then I'm accessing again locations that are nearby, and then I put some more on, and so on and so forth. So when I access the locations that are nearby, what that represents is basically my local variable access on my stack. And what do these diagonal lines represent on the stack? What am I doing every time I have one of those diagonal lines? I'm putting something new on the stack, and when do I do that? Yeah?
Calling a function?
Yeah, when I make procedure calls, exactly, okay? So each one of those diagonal lines corresponds to a procedure call, okay? But what you want to see from here is that once again, you know, the locations that we're accessing are close to each other, and the location, and when we access a particular location, we often will access it again shortly after. Okay? Now let's look at our third type of value that we find in memory, which is our data. And here what we've got, if you look at these diagonal lines over here, this would correspond, can anybody tell me what that would correspond to if it's data? So these are memory locations that are right next to each other. An array, exactly. So these are our array accesses. Okay, so basically what I'm seeing here is that for my code, my stack, and my data, I'm seeing the same phenomenon. One thing that I'm seeing is that if I access something recently, I'm likely to access it again in the near future. And the second is that if I'm accessing something, I'm likely to access something that's nearby in the address space. Okay? And so essentially the way that we summarize that is we call this locality. So we have two forms of locality. One is called temporal locality, and the other is spatial locality. So temporal locality basically tells you that if I'm accessing a particular location right now, I'm very likely to access it again in the near future. Okay? So we saw that come to play, for example, when we executed loops in our code, right? We go back and we execute the same instruction over and over. Spatial locality says if I'm accessing a particular location in memory, I'm very likely to also access another location that's nearby. Okay? And so that's going to come into play when, I access arrays, or when I'm accessing my stack. I'm always accessing things that are nearby. Okay? And similarly with my code, if I'm just proceeding sequentially through my code, then I'm getting one instruction after the next, all of which are close to each other in my instruction memory. Okay, so how do we make use of these, predictable patterns? Well, what we're going to do is the following. We're basically going to cache the information that we recently accessed into this faster memory, which we call a cache. Okay, so what do I mean by that? So essentially what's going to happen is imagine that I just have, a two-level hierarchy right now. So here's my, here's my processor, and it's trying to get something from memory. So when I try to get something from memory, the first thing that I'm going to do is I'm going to try to get it from this fast memory, like this SRAM memory, which we call a cache. If the data is there, then I get it back very quickly. If it's not there, then I go to the next slower memory and try to fetch it from there. Okay? So suppose that, I'm trying to fetch a particular address. If every time I fetch a particular address, I go and I bring that address into my cache, then because of locality, it's going to be likely that I'm going to try to access that location again in the near future. So the first time I try to access it, I'm not going to find it in my cache, and I'm going to pay for taking longer to get it from my main memory. But if I then brought it into my cache, then the next time that I try to access that location, I'm going to get it much more quickly. Okay? So essentially, it's summarized as follows. So when I try to fetch something from my cache, either I can get a cache hit because it was actually there, in which case I get it back quickly, or I can get a cache miss because the data is not there. So in the case of a cache miss, I'm going to go fetch the data from my slower main memory, but I'm going to bring a copy of it into my cache so that the next time that I access it, because of either temporal or spatial locality, I'm actually going to get a hit when I look for it in my cache. Okay, and so once again, remember that because of this behavior, the CPU has to be able to tolerate variable latencies from memory. Sometimes it's going to get the data very quickly because it found it in the cache. Sometimes it's going to take longer because it has to go to one of these backup memories. Okay, so now that we understand this concept of locality and how we want to go about using caches in order to try to improve our access time for things that we're accessing on a regular basis, This is basically what a typical memory hierarchy is going to look like. So essentially, as you've already seen, on the data path or on the CPU itself, you're going to have a bunch of registers which are very fast and they're going to be used for all of your computations. Then on the same chip as your CPU, you're going to have potentially multiple different levels of caches, where this level 1 cache is the smallest, and so it's also the fastest. Then the level 2 is a little bit bigger, but also now takes 10 cycles instead of 2 to 4 cycles, and so on, okay? And so every time we go to look for something in memory, we always start, at the top and work our way down this table. And as we go down the table, then we have both increased capacity, but also increased delay. All right. So for the last couple of minutes, what I want to talk about is, how do we know basically if our cache is helping us, okay? So we have certain cache metrics that we use. And so first let's define what they are. So we have something which is the hit ratio. Hit ratio is telling me what fraction of the time when I go to look for a particular address in my cache, do I actually find it there, okay? And so the hit ratio is calculated basically by taking the number of hits that I have in my cache divided by the number of hits plus misses, or divided by the total number of accesses, okay? What about my miss ratio? Well, my miss ratio is just 1 minus my hit ratio, right? Or another way of thinking about it, it's the number of misses divided by my total number of accesses, okay? So what do I use these ratios for? What I use them for is to measure this important metric, which we call average memory access time. So what is average memory access time? It's basically telling me, on average, how long is it taking me to access memory, okay? And so this is going to take into consideration the fact that sometimes I'm going to get a hit in my cache and I'm going to get the data back very quickly. And sometimes I'm going to get a miss in my cache, and so I have to go to my secondary memory and it's going to take longer. Okay, so what is my average memory access time? It's basically my hit time, because I always have to check, does my cache have the piece of data that I'm looking for? And then if I didn't find it in my cache, which is going to happen miss ratio fraction of the time, then I'm going to pay this miss penalty, which is how long it takes me to now go and access main memory. Any questions about where that equation comes from? Okay, and so if we have, multiple levels of hierarchy, then I can just apply the same equation recursively, okay? And so I can, calculate what the average memory access time is regardless of the configuration of my memories. Okay, so now we want to ask ourselves a question. So let's say, that I have this simple memory configuration where I have just one cache or one level cache, and then I have a main memory. And my cache is going to take 4 cycles, but accessing my main memory is going to take 100 cycles. Okay? So the first question I want to ask myself is, how high does my hit rate have to be so that adding this cache between my CPU and main memory does no worse than if my cache wasn't there? Okay? So if I didn't have a cache, every single time I accessed main memory, it would take me how long to access it? If I didn't have a cache, I have to go to main memory, which takes 100 cycles, okay? So I'm basically saying figure out what the hit rate has to be in order to end up with an average memory access time of 100. Okay? So we plug in here our hit time, which is the time it takes to access the cache, is 4. Our miss rate is 1 minus our hit rate. And our miss penalty is the amount of time it takes us to access the memory. Okay? And so if we solve for our hit ratio, we get 4%. Which is really pretty low, right? So I only have to, get a hit in my cache a very small percentage of the time for it to be worthwhile from a performance perspective to have added this cache to my system, okay? Now let's ask ourselves a second question. Well, suppose, I'm not satisfied with being as good as if I didn't have my cache, and instead, I want my performance to be almost as good as if I always got a hit in my cache, right? So if I always got a hit in my cache, my average memory access time would be 4. If I almost always get, let's say it's going to be 5. Okay, so now if I solve for my hit ratio so that I can end up with an average memory access time of 5, I find that I need a hit ratio of 99%. Okay, now this seems very high, and it is, but it turns out that because of locality, it's actually very feasible to get very, very high hit rates in our caches. And so our caches are actually able to dramatically improve the average memory access time of our memory systems. So just to conclude, and you're going to see more detail of this in tomorrow's recitation, which will then go over again in Thursday's lecture. But basically, I just want to introduce what a cache algorithm looks like. So at a high level, we said that we're placing this cache between our CPU and our main memory. The cache is small, so it's not able to store every single memory location. So when I put something into the cache, not only do I need to put the data that it's storing, but I also need to put some information about the address from where the data came. Okay, and so that's what's referred to here by the tag. So the tag is telling me where did this data come from, and then the data is the data itself. Okay, so now when I go to access my cache, one of two things can happen. I can get a hit, and a hit means that if I was looking for address X, one of my tags was in fact X, and so then I can return the data that's in that same row, which is, the data that, the memory of X. Alternatively, however, if I look through my entire cache and I didn't find X in any of the tags, that means that I got a miss. And so now, if I got a miss, I have to go fetch that location from main memory. So I'm going to do the following. I'm going to first read the value of address X from main memory. I'm going to return that value because that's what my CPU is waiting for. I'm going to then pick a line in my cache where I'm now going to store this value so that if I try to access it again, next time I'm going to get a hit in my cache. And so then I go ahead and I write the tag of the line that I picked to be X, and I write the data of that row to be memory of X. So now next time I come and I look for the same address X, it's going to be in my cache and I'm going to get a hit. Okay? So we're going to do a lot of work with this. You're going to see, start to see some examples of this in tomorrow's recitation, and then lots and lots of examples in Friday's recitation after we go through all the different kinds of permutations of how to implement our caches. All right, thanks everybody.